We finally come to a measure of dispersion which is by far the most useful and by far the most popular measure of dispersion, the standard deviation. It is defined as the square root of, it is the square root of the sum, the square root of the arithmetic mean of the squares of the deviations from the arithmetic mean of the data. Generally, it is denoted by this Greek letter called sigma. So, for raw data, your sigma will be square root of the arithmetic mean of the sum of squares of deviation, or the arithmetic mean of the squares of deviation. So, your deviation from arithmetic mean is x minus x bar. It is squared, and the mean of xi minus x bar will be like that. So it is the square root of summation xi minus x bar whole square divided by n. And if you have frequency based data, the same thing can be bonified as square root of summation of frequency times xi minus xi minus x bar whole square divided by n. The square of standard deviation, that is sigma squared, is called variance of data, and standard deviation is called the positive square root of sigma square. Let's try and use that formula in this example. You have raw data or individual observations, 7 observations of x, which I have listed down here. The first step you need to do is find x bar. X bar will be summation of x divided by n. So summation of x will be 231. So your arithmetic mean is 231 divided by 7, which is 33. Your deviations will be xi or xi minus x bar, which is 33. So this time, remember, we are not ignoring the signs. So this is minus 10, minus 8, minus 5, minus 2, 38 minus 33 is 5, 40 minus 33 is 7, 46 minus 33 is 13. Your formula for standard deviation or sigma is square root of arithmetic mean, that is summation of deviation squared divided by n. So now I need to find xi minus x bar the whole squared, where x bar is actually 33. So minus 10 whole square is 100, 8 whole square is 64, 5 square is minus 5 square is 25, 4, 25, 49 and 169, all of which add up to 436. So putting them into the formula, you will get root under 436 divided by 7, which when you use your calculator you will get 7.89. This is example 10 from the guide. Now, point to be noted is you have a simpler version of the same formula. It is called the simplified formula. A simplified version for standard deviation, which is summation xi square by n minus x bar square. And if you have a frequency distribution data, you can write the same thing as summation fxi square by capital N, where capital N is actually your total number of observation minus summation f x by n whole square. Okay, just to point out, since the I is understood, I think in the book they are just writing it as fx square. So xi would mean each individual value of x. They're just ignoring the I subscript. Now, this simplified formula is actually derived from the original version that I wrote earlier, that is sigma equals to square root of xi minus x bar the whole square, summation xi minus x bar the whole square divided by n. So when you expand that formula, you can actually derive these equations. Like I said, this would be for individual raw data, and this would be for a frequency distribution data. But these both these formulas are involve a lot of calculations, especially if your x values are quite big, then squaring them becomes quite painful. So you can actually use the shortcut method. If you remember, even for the arithmetic mean, we have studied the shortcut method, where what you do is you calculate d, which is x minus a, that is deviation of the x from either an assumed mean or it could even be from the arithmetic mean. Okay, so once you've got d, your formula for standard deviation becomes summation d square by n minus summation d by n, that is the mean value, the whole square. Look at both these formulas, they're very similar. Instead of x and x bar, I'm writing it in terms of d and d bar, or mean value of d. Okay, now for frequency data in the shortcut method, I can write a similar formula using d. It will be summation f times d square divided by capital N. I'm writing capital N because it denotes the total frequency, minus summation of f into d by n whole square. Now, if you have got a continuous series frequency distribution, that is, you have got class intervals 0 to 10, 10 to 20 and so on, and you have the corresponding frequency, you can actually modify the d. This would be a step deviation method. It's called the step deviation method. They haven't mentioned the name of this method, but yeah, in step deviation method, your d is x minus a divided by c, where c is the class interval, the size of the class interval. And then you proceed to use the same two formulas as given above. Okay, so this is the step deviation method. In the shortcut method, it is simply x minus a. In the step deviation method, it's x minus a divided by c, where c is your size of the class interval. So your sigma formula can be slightly modified, very small, summation f d square by n minus summation f into d by n the whole square into c. The c is outside the root. Okay. Now we shall have a look at examples of solving these. Earlier we looked at calculation of standard deviation for individual observations using the original and the simplest formula. Now let's look at calculation of standard deviation for, again, individual observations, but we're using the shortcut method. So remember, in shortcut method we define a variable called d, which is x minus a, where a is your assumed mean. Over here, if you notice, the middle observation is 50, and we can always take a to be 50. You have the freedom to take any of these, or you can even take the arithmetic mean of these 5 observations to be your assumed mean. The only thing is, if I take the arithmetic mean in this case, it might be a decimal point, and I don't want to complicate the numbers. So I'm going to write d as equal to x minus 50. So remember, the signs are very important here. You do not ignore them. So 42 minus 50 is minus 8. 48 minus 50 is 2. 50 minus 50 is 0. 62 minus 50 is 12. 65 minus 50 is 15. Right? And I also need my d square, which is 64, 4, 0, 144 and 225. Now my formula when you are using the shortcut method is root under summation d square by n minus summation d by n squared. Okay, so I need summation d as well as summation d square. Now summation d comes out to be a small value because the top two values are negative, so that's 17. Summation d square will be positive and it will come up to be 437. your number of observations n is equal to 5. So sigma is 437 divided by 5 minus 17 by 5 the whole square. Which will be 8.70, or actually 8.71, because when you round it off, that's what you get. So this is how you will calculate your standard deviation using the shortcut method. Now let us calculate the standard deviation for a discrete frequency distribution, which means you have an x value, which is a point value like 10, 12, 14, 16 and 18, and you have the corresponding frequency given to you in the frequency table. So first let's use the simplified formula. If you remember the simplified formula, it is summation fx square by n, where n is your total frequency or total number of observations, minus summation fx by n, which is squared, right? So we need fx, 10 into 220, that is basically these two columns are multiplied, so you get 48, 140, 48 again, and 18, and you will need summation fx, so if you add it up you will get 274. Your n will be nothing but total frequency, so that's 20. Now you also need fx square, so let's just calculate x square. So your x square column reads like this, and then you need f times x square, which is basically these two columns being multiplied. So you've got 200, 144 times 4 will be, okay, so sorry, 76, 768, all of which add up to be 3828. So your sigma will be divided by 20 minus 274 divided by 20 squared, which, use your calculator and confirm. Okay, now I just want to show you that using the the shortcut method simplifies these calculations. So I'm going to work with the same example and use the shortcut method. So once again, let me just copy down the value. So now I'm using the same discrete frequency distribution, but this time I'm going to use the shortcut method. If you remember, in the shortcut method we define a variable called d, which is x minus an assumed mean a. I'm going to use one of the central, okay, since we have 5 x's, I'm going to use the middle value 14 as my assumed mean. So d is equal to x minus 14. So 10 minus 14 is minus 4, 12 minus 14 is minus 2, 14 minus 14 0, positive 2, and 18 minus 14 is positive 4. You will also need d square, so that's 16, 4, 0, 4, 16. Now remember the formula looks like this: summation f times d square divided by total n minus summation f times d divided by total n squared. Right? So I need to figure out some more space. I need some more space. Hang on. Right, I just made some bit more space. So I need fd square, my next column. I need fd, and I also need f times d square. So fd means f and these two columns being multiplied. So f times d is right, minus 8, minus 8, 0, 6, 4. It will sum up to be minus 6. And f times d square means this multiplied by this column. So I will get 2 into 16 is 32, 4 into 4 is 16, 10 into 0 is 0, 3 into 4, 12, 1 into 16 is 16. So you got 32. Your n is total frequency, which is equal to 20. So putting all this into the formula, we get sigma as root under 76 divided by 20 minus 6 divided by 20 the whole square, which is equal to, so you can confirm with your calculator that this will come up to root under 3.71, which is equal to 1.92. So as you can see, the advantage of this shortcut method is that I'm getting simpler numbers and smaller products to add up, right?